So students, in this section of video, let us understand the vibrations executed by a spring. Vibrations executed by a spring, or sometimes called mechanical vibrations. So as I told you, in this module SHM, we are discussing all the possible kinds of simple harmonic motion. So in the previous video, it was a general introduction to what is a simple harmonic motion. And in this case, let us understand the simple harmonic motion in the case of a spring. Okay. Now in this case, we are considering a spring which is fixed at one end to a rigid support and other end is left free, or a mass is attached to the spring. So if I just pluck the string and leave it off, we know that the spring vibrates in both the directions and gradually comes to halt. So I can consider vibrations of a spring also as a simple harmonic motion. Now in this case, how is it a simple harmonic motion? If this is the spring, so let me consider if a mass of m is attached to its free end. There could be a mass m attached, or it could be a free end on the other side. Let me consider this as my equilibrium position or my reference point. So if I pull the mass downwards and left it free, we know that the spring vibrates and gradually comes to rest. That means what? If I just pull the spring would have been expanded like this. And the point P has come here. So the spring expands and contracts. So once it is expanded, the next time it is contracted. And the point P has come here. So when I just pull the spring, which is attached to a load at free end, and leave it free, the spring expands and contracts and gradually comes to its equilibrium position. So what do I mean by that? In this case, when the spring is expanded, it is expanded by a distance, say x1. And when the same spring is contracted, I can say it is contracted by a distance x2. So because there is expansion, there is also a restoring force. That restoring force tries to bring the spring to its equilibrium position at this point. So in the case of x1, what is the direction of restoring force? F1, upwards. So the restoring force is pushing the spring back to its equilibrium position. So this is the equilibrium position. In the case of contraction, the spring is contracted and hence it has moved up. So this much is a displacement from the equilibrium position. So in this case, the spring experiences a restoring force in this direction, so that the P comes to this point. So I can say whether the spring expands or contracts, it experiences restoring forces F1 and F2 acting on it. Now, this I can give as a good example of simple harmonic motion, because the vibrations are on both the sides of equilibrium position and there is a constant restoring force acting on it. Now, before we understand this kind of oscillations, let us make some assumptions, because if I don't make assumptions, I may have to consider many other parameters into consideration. So let me assume that the spring is light in weight. So spring is light. I am not considering the weight of the spring. If I add the weight of the spring, that will also add up to the total mass. So let me assume spring is lightweight. And the second assumption is the restoring force is proportional to the extension in the spring. Extension in the spring. What do I mean by that? Say in this case, the extension in the spring is x1. So how much is the value of the force F1? It should be equal to the magnitude of x1. So more the extension, more restoring force. Less the extension, less the restoring force. I can say restoring force depends on the extension. Now based on this, we have to know a very important parameter. So let me say this is the spring. So I'll redraw the same diagram here. So this is the spring in the absence of load. So instead of drawing all the three diagrams, what I mentioned above, let me draw only two diagrams for our understanding. So in the presence of load, the spring is extended. So the point P has come here. So what is the extension in the spring? X. Let me say X is the extension in the spring. So we know that the restoring force is proportional to extension in this case, in the case of the spring. So I can say restoring force is proportional to extension. So what is the direction of restoring force in this case? The restoring force is acting upwards because this should come back to the original point P. So I can say minus X. Or what is the magnitude of restoring force? Magnitude is proportional to distance, only the direction is opposite. So when I remove the proportionality sign, I have to replace by a constant. So let me say the constant is K. Okay. So what is K? K is called spring constant or sometimes stiffness factor. So what is K? K is equal to F by X. So how do I define spring constant? It is for a unit extension, how much is the force experienced by the spring? Or in other words, it is the extension undergone by a spring unit extension for a force of 1 Newton. Say for example, I am applying a force of 1 Newton and a unit extension, say 1 meter or 1 centimeter is the extension in the spring. So this ratio is called stiffness factor or spring constant. The unit of spring constant is Newton per meter. So spring constant is a very important parameter. As we have written here, it is called stiffness factor. So spring constant tells us how strong is the spring, how much load it can withstand. Our common example, say if I have a very small weak spring here and I have a very and if I have another thick spring, if I have another thick spring,